Let's take a look at Q1 from section 3.2. In this example, we've been given a coefficient A matrix, we've been given a possible eigenvector, and we would like to use the defining statement for eigenvectors and eigenvalues to attempt to verify whether or not this is, in fact, an eigenvector of this system described by our coefficients here. To do this, we just need to substitute our A and our V into our definition statement for eigenvectors and eigenvalues, which looks like so in this case, we know A, we know V, we don't yet know lambda. What we're wondering is it possible that 6, negative 2 is an eigenvector here? If we can find its associated eigenvalue, then we would be convinced that it is in fact an eigenvector. Here we just got to do the matrix multiplication on the left. 4 times 6 is 24. 3 times negative 2 is negative 6. 24 minus 6 will leave us with 18. On the bottom, negative 1 times 6 is negative 6. 0 times negative 2 is 0, so we're going to get a negative 6 on the bottom. Now we're going to ask ourselves the question, is there some constant lambda that can make this statement true? What we can see is that this vector on the right, 6, negative 2, is in fact a constant multiple of the vector on the left, 18, negative 6. Hopefully by visual inspection we can tell here that lambda equals 3 is the eigenvalue, so I should go ahead and give that a 1, that is associated with the eigenvector of v1, 6, negative 2. Before we walk away from this example, I'd just like to point out two other possible scenarios. One possible scenario is that our vector on the left became something like 18, negative 5. If that would have been a negative 5 down here, then there's no way for me to just take constant multiples of 6, negative 2 to arrive at this value. Therefore, whatever vector was used, if we were to arrive at 18, negative 5, the vector associated with that computation would not have been an eigenvector. On the other hand, you should notice that if we had instead for v1 used the vector 3, negative 1, we would have actually arrived at an equivalent statement to this over here that would have also given us the same eigenvalue of 3. We want to remember that if you have found one eigenvector, you have found an infinite number of eigenvectors. Any constant multiple of an eigenvector is also an eigenvector associated with that eigenvalue. In vector land, we should be picturing the fact that all of these vectors here that are all constant multiples of each other are all pointing in the same direction. They in a sense just have a different strength or speed that might be associated with them there. But we are interested in finding all vectors in a sense that are collinear with this to name them collectively as the eigenvector associated with that system, one of the eigenvectors associated with that system.